Hey everyone, and welcome. Today we are going deep into the world of fire protection engineering. We're going to follow the entire journey of a firefighting system, starting with something that looks as simple as this, an engineering drawing, and watch how it transforms into a life-saving installation that protects an entire building. All right, let's get into it.
So it all really boils down to this one question. How on earth does a flat, two-dimensional plan, just a bunch of lines and symbols on paper, become a real, working, three-dimensional system that we trust with our lives? That whole journey, from the blueprint to the final build, is exactly what we're going to break down right now.
So here's our roadmap. We'll kick things off by learning to read the language of the design itself. Then we'll get into the engineering logic behind sizing all the components. We'll take a look at special systems like the FM200, see how a design actually gets a price tag, and then follow the action on site with execution and testing. And finally, we'll wrap it all up with the approval process and the one big idea you should take away from all this.
Okay, first things first. Before you can build anything, before you can price anything, you have to be able to speak the language. And that means reading the engineering blueprint. This is the foundation, the source code for the entire project.
So when you look at a drawing, the first thing you do is a quick inventory. What are we dealing with here? Well, the drawing tells us it's a wet firefighting system. Pretty straightforward. That just means the pipes are always full of water ready to go. We can spot the fire pump room, and hey, there are 3 pumps, an electric, a diesel, and a jockey. We also see a special FM200 system. That's a clean agent, a gas, used for places like server rooms where dumping water would be a disaster. And finally, it notes the fire alarm system is for integration only, meaning we just need to make sure our system talks to it.
Let's follow the water. It's a really simple, logical path. It starts in a massive water tank, gets pulled into a big common pipe called a suction header. Then it hits the pumps where it gets pressurized. From there, it's shoved into the discharge header, and finally it's sent out into the building-wide network of pipes. It's a one-way trip from storage to suppression.
Now, these drawings are packed with visual clues to make life easier. See all the red pipes? That's your instant giveaway that you're looking at the firefighting network. You'll also see arrows all over the place showing you exactly which way the water is supposed to flow, and a whole language of symbols for all the different valves and gauges that control everything.
So, now that we can read the map, let's talk about how the map was made. This is where the real engineering kicks in. Nothing you see here is a guess. Every single component, every pipe, every valve has its size determined by very specific calculations, all laid out in international standards.
And those standards have a name, NFPA, the National Fire Protection Association. They literally write the rule books for this stuff. Codes like NFPA13 for sprinklers, 14 for standpipes, and 20 for the pump room. These tell engineers precisely how to do the math to figure out the exact pipe diameters they need based on how much water has to flow and at what pressure.
But here's a super important detail. Not all pipes are sized the same way. The pipe that feeds water to the pump, the suction pipe, is designed completely differently from the one that leaves it. On the suction side, the goal is to have the water move really, really slowly, so you use a bigger pipe. Why? To prevent something nasty called cavitation. That's where tiny vacuum bubbles form in the water and then violently collapse inside the pump. It's like setting off microscopic explosions that will literally eat the pump from the inside out. The discharge pipe, on the other hand, is all about handling the high pressure and flow needed to get the job done.
Now, all those little symbols for valves, each one has a critical job. You've got OS and Y, or butterfly valves, which are basically the on-off switches for isolating parts of the system when you need to do maintenance. Then you have check valves. Think of them as one-way doors that make sure water can't flow backward. The alarm check valve? That's the snitch. As soon as water starts flowing, it sends a signal to the fire alarm panel. And of course, you've got relief valves, which are the ultimate safety feature to prevent the system from blowing itself apart from too much pressure.
And all of that brings us to the absolute heart of the system, the fire pumps. Picking the right pumps is a huge deal. It's a delicate balancing act, and it's probably the single most important decision in the entire design.
So here's the core philosophy. A fire pump isn't just about moving a lot of water. That's flow, measured in gallons per minute. It's about moving that water with enough force. That's pressure, or PSI. The pump has to be strong enough to shove all that water up to the very highest sprinkler in the building, fighting against gravity and the friction inside the pipes the entire way. It has to deliver the flow at the required pressure.
And that's exactly why you see 3 of them. Think of it as a team. The little jockey pump is there to handle tiny pressure leaks and keep the system topped up, so the big guys don't have to turn on all the time. But if a sprinkler head actually goes off, the pressure drops in a big way. That's the cue for the main electric pump to roar to life. And what if the power's out? No problem. If the electric pump doesn't start, the big diesel engine kicks in as the ultimate fail-safe backup.
Okay, so water is great for most fires. But what about those special areas, like a data center or a room full of priceless archives, where water would do just as much damage as the fire itself? Well, that's where these special systems, like FM200, come into play.
But that creates a whole new engineering puzzle, right? It's not about flow and pressure anymore. If you're flooding a room with gas to put out a fire, how do you know exactly how much gas you need? Too little and the fire doesn't go out. Too much is just a waste of money.
Well, the answer comes from a surprisingly simple formula, which is laid out in the NFPA13 standard. You just calculate the exact volume of the room you're protecting in cubic meters. Then you multiply that by a specific design percentage, which depends on what you're trying to protect. And boom, that gives you the precise weight of FM200 agent you need down to the kilogram.
So, we've got the design figured out, all the calculations are done. What's next? Well, now we have to turn all this engineering work into a real-world shopping list. It's time to find out how much this is all going to cost. And that is done with something called a bill of quantities, or a BOQ. It's exactly what it sounds like. You literally go through the drawing with a fine-tooth comb and count everything. Okay, how many meters of 150mm pipe do we need? 25. How many gate valves that size? 4. Every single nut, bolt, valve, and pipe gets identified, counted, and put on the list.
And here's why that's so critical. Every single decision made back in the design phase has a direct, cold, hard financial impact. If an engineer decides to upsize a pipe by just one size, the BOQ changes and the cost goes up. If they add one extra valve, the budget changes. The design is the budget, plain and simple.
All right, the design is approved, the materials are on their way. Now we finally get to leave the office and head to the construction site. This is where the 2D plan finally starts to look like a real 3D system.
And you can't just start bolting things together. There is a very specific, very logical order of operations. First, you pour the concrete bases for the pumps. Then, you install the main pipes, the headers. After that, you carefully place and align the heavy pumps on their bases. Only then do you connect the valves and flanges. It's a step-by-step process that makes sure everything lines up perfectly and operates without any stress on the equipment. Once it's all built, you have to prove it works. The NFPA requires a whole battery of tests. You fill the entire system with water at high pressure to make sure there are 0 leaks. You flush it out to get rid of any dirt or debris left over from construction. You run the pumps at full blast to prove they can deliver the flow and pressure they were designed for. And you test every single alarm to make sure it sends the right signal to the right place. And finally, all of that hard work, the original drawings, all the complex calculations, the bill of quantities, photos from the installation, and all those testing reports, it all gets compiled into one final massive submittal package. This is the proof. This is the evidence that the system was designed correctly and built to that design.
Which brings us to our final and most important takeaway. Fire protection isn't just a set of drawings. It's a whole process. It's the careful sizing based on proven standards. It's the detailed calculations that back up the design. It's the quality of the work on site, and it's the rigorous testing that verifies it all. Every single one of those steps is absolutely essential to turn a simple blueprint into a system that you can truly trust to save lives.